Saw in our earlier video that when we have a ray of light represented here in the blue arrow, we have a ray of light that goes from one medium, which is in the salmon color, into a different medium, that's the lime green. The light will bend. We've also probably noticed that you're going to get a little bit of reflection going on here as well. Okay, but what we're going to do is we're going to focus on for now is the bending of the light. And what we know is that the the amount that it bends is determined by the comparison of the two index refractions. Okay, so if it goes into a less dense material, it tends to move more this way, away from the normal line. And if it goes to a more dense material, it goes towards the normal line. So if it speeds up, it goes this way. If it slows down, it goes this way. Okay. Otherwise, it would just go straight if it had the same index of refraction. Okay. So here we're going to go into one that has, here the green has a smaller value. As an example, maybe what we have here is we have maybe n equals 2, and down here maybe we have n equal to 1. So it's speeding up and it's moving away from the normal line. As opposed to this example, maybe this is n equals 1 and this is n equal to 2. As I shine my laser through this material, you can see that there's light traveling through it. And if you were to look carefully from above, you would see that it is refracted. It is entering sort of on this path, but it's coming out on this path. But you'll also notice that there are two lines over here of reflection. One is reflecting off this first surface. The second one's actually reflecting off the second surface and coming out over here. The other thing you should notice is that the line on this side is much more intense than the light being reflected. And the intensity, if you were to compare the intensity to this side to the intensity on that side, it is going to change. As I approach 90 degrees, you can barely see the reflection. It gets lighter and lighter, and the refracted light gets brighter and brighter. The opposite is also true. As I increase the angle of incidence, you'll notice that the reflection gets brighter and the refraction gets lighter. And then there becomes a critical angle when it all changes. Here I show three different light rays coming in through a boundary, the boundary being the solid black line. So I've got a red line coming in, a green line coming in, a blue line coming in. And they don't represent different wavelengths. I'm just trying to indicate three different rays of light coming in. And the top material has an index of 1.5, and the bottom one has an index of 1. Just some nice, easy numbers for us to think about. So what's going to happen as these lights come in? Well, because the top one is bigger than the bottom one, what we're going to witness is we're going to see a bending of light. Remember, if they were the same number, the light would go straight. If the bottom number was bigger, it would go this way. But the bottom number is smaller, so it's going to bend that way. Now, I haven't figured out exactly how much yet, but I can using Snell's law. But for now, let's just think about what's going to happen. So here's the green one. Once again, it's also going to bend this way. What about the blue line? Well, the blue line here is going to bend this way. And it's kind of interesting that it snaps right into place here on top of my x-axis, okay, which is the boundary between. So what happens is there becomes a certain angle, a critical angle, where we no longer have this refraction going on, but it actually just travels, the light travels through the medium here, through this boundary of the medium. So we don't get much reflection. Remember, we talked about a moment ago is that we would have some reflection going on. We're not seeing this, okay? Because as we as this happens, what goes on with this line here is that this arrow also becomes more and more or closer and closer to this axis. So as the angle decreases, this line becomes closer and closer and closer to the x-axis. So, and I'm calling it the x-axis, but it's really the boundary between these two mediums. And so as your reflection decreases, so does your refraction. And once again, what we see is we see that the light just travels down through the boundary here. Okay, so the question we're asking is, what is this angle here? Now, of course, that's not our angle of incidence. Remember, the angle of incidence would be this angle here. And so what we want to know is we want to know what is the angle of incidence. We want to know that angle there. What angle would make that happen? We also should think about what is this angle here? And this angle here is 90 degrees. So anytime you're trying to figure out the critical angle, what we're looking at, the critical angle is in relation to 90 degrees. This will not happen if the one on top is smaller. So if this was smaller than the one on the bottom, let's just say it was reversed. If this was 1.5 and this was 1.0, it wouldn't happen because instead of getting closer to here, it's going to get closer to here. So that won't happen under those conditions. Okay. We know that to solve this angle, we would have the n times the sine value of the incidence equals the n times the sine value of the refraction. And I want to point out that this is going to always be the sine of 90 degrees. And what is the sine of 90 degrees? The sine of 90 degrees is exactly 1. Okay, it's exactly 1. So what we're going to have here is we are always going to have the n of the refracted material times the sine. Oops, sorry, I said refracted material. Sorry, it is the incidence material, the first one, times the sine of the angle of incidence, and that equals the n of the refracted, times 1. Okay, so I don't really need to write in that times 1 because times 1 is just going to be nr. So to find the angle, okay, the sine theta of the angle is always going to be the ratio of the nr over the ni. So in this example, that would be that the sine of the angle is going to be 1.0 divided by 1.5. Okay, and when we divide that, I can do that in my head. That's 2/3. So sine theta equals 0.66666666. Eventually, I'll round that off to 7. And we can find out that this angle of incidence in this particular example is 41.8 degrees. That is what we call our critical angle. Okay, so what is that saying? That is saying that once this hits 41.8 degrees, we're going to get this light is not going to travel into the second medium here, which whatever it was, it's going to travel along this surface. And if we increase that angle, if we made that beyond, what was the angle here? 41.8 degrees. 41.8 degrees is our critical angle. If we increase the angle beyond 41.8, the light will never escape. It'll just travel on that way forever. If we made that angle less, we put it in here, let's say at 40 degrees, and we pull that back a little bit, and at 40 degrees, we will have a little bit of refraction, and there'll be a little bit of reflection as well. Okay? So that's what this angle is telling us. Really important. It's called a critical angle. Okay. Let's do a practice question. So what is the critical angle as light tries to escape a diamond into air? Okay, so we found that the easy thing for me is I'm just going to go right to my formula here because I have a formula that's going to work every time, but we could derive that if we want. In fact, why don't I just go back? I'm going to go Ni times the sine equals Nr times the sine. And I've got Ni. Well, we know what Ni is. It's given to us there. It's the diamond. So 2.43 times the sine of the angle, don't know the angle, equals 1.00029 times the sine of 90 degrees. But we already know that the sine of 90 degrees is 1. So the sine of the angle here would be equal to 1.00029 divided by 2.43. That one I'll use a calculator on, and I'm seeing an answer here of 0.4116. And therefore, my critical angle for diamond going into air is 24.3 degrees. Okay, so that's the critical angle diamond to air. And what that is that's pretty interesting because it's a small angle. And that's partly because the density of the diamond, it's so dense and it's hard for the light to escape. And that's why diamonds are so beautiful is when you look at them, you get this glare, this special twinkling of the light. And that's because that, and it's even better when you cut diamonds a certain way. But what happens is that you've got this diamond and the light comes in and it gets reflected off, and it's gonna get stuck inside this material, and it gives this beautiful color to it. We can see all the light moving around inside. Okay, so first question: what is the critical angle? I think we said it was 24.3 degrees. What happens at angles larger than that? Okay, light stays in. Okay, and what happens at angles smaller than that critical angle? Then it gets refracted out. Okay, so again, it gets bent. But 24.3 degrees is that angle where things change. So scientists and inventors have taken this knowledge and they've applied it to a number of things. And one very common thing that is really taking over is that they found that because light moves so quickly, right? We're talking 3 times 10 to the 8th meters per second. What they've done is they've actually made plastic plastic wires. And what they do is they shine light in at certain angles. So, this one's coming here at an angle and it cannot escape because we're beyond that critical angle. It never, never, never escapes. And this is basically referred to as we've got, and I didn't use this word earlier, it is internal. Okay, we've got this internal reflection. And that's what's happening when it's going down through, in this example here, this is what's going on is we've got, essentially it's bouncing back and forth through this medium here, and it doesn't ever escape. Okay, so that's our internal reflection. In fact, it's referred to as a total internal reflection, meaning that it never escapes. And so the light just keeps bouncing through, and you can send multiple signals down through this wire, this plastic wire, and the light never escapes, and it just keeps going. And it's actually faster than electrons through a copper wire. It's bendable, it's flexible, there are certain, and you can't turn 90 degrees with fiber op. You can't take it and bend it around a corner. That doesn't work. But you can do these sort of smooth turns. Um, another thing that they use prisms for. So, for instance, you could have um, binoculars use these, or telescopes use these. But let's say you are building some kind of periscope. Okay, so let's say that you're going to look in here. Let's say you're you're in a submarine, and you're trying to look out, and you're trying to see if there's an enemy ship up above the water here. Here's the water, and you want to know if there's an enemy boat out here of some sort, right? Sailboat, yeah, submarines and sailboats. That's not quite accurate, but anyway, you want to know. So what they've actually done, what they used to do is they used to put mirrors here. They would put a mirror here. They would put a mirror here. The problem with mirrors is that somewhere around 5 to 15% is actually absorbed. A lot of this light energy, when the wave of light hits this, some of it gets absorbed into the mirror, and then some of it will go up here and get absorbed by this mirror. So when you get this image of the boat, it's not very bright, or it's not very clear. But what they're doing now is they're actually replacing the mirrors with prisms. And they're getting, because these don't have that 5 to 10% loss. Okay. So mirror has a I said 5 to 15% earlier, 5 to 15% loss due to being absorbed, loss to absorption. Okay. And they're finding that with fiber ops and using critical angles and so on, it's less than 2%. So you're getting brighter images and more clear pictures. So that's why in telescopes they're using this, so they can look at distant galaxies, or binoculars if you're somebody outside using binoculars.